Hey, hi guys. This is another workshop related to functional programming in Scala. So let me share my screen. Can you see my screen now?
Yeah.
Yeah.
Okay. The font is okay for the terminal.
Yeah.
Yes, it's
Cool.
okay.
Awesome. So, well, today we are gonna talk about some other concepts regarding to functional stuff. Today we are gonna talk about two algebraic data types and how we can use to model data using pure functional stuff. Also, we are going to talk about functions and in deep. And yeah, this is the idea for today. So, algebraic data types has an acronym ADT. Uh, in the programming world exists other concept with the same acronym, abstract data type. Uh, Make sure that when you find something, you refer to algebraic if you know a little bit more. So this is a functional pattern that allows modeling data, usually called domains, in terms of logical ORs and ANDs. You know, let's try to see this in an example. There are two ways to express algebraic data types. One is sum times pattern and product types pattern. This is the idea. For instance, we have a type B, a type T, and we have this is the definition for product type. Okay? This class. Here we go. A product type parent, it's a way to model data that contains other data. You know, it's per se this class A contains an specification for B and C. Okay, we can also define in this way. This is another alternative to define when uh, an A has B and C. That means when you create an instance of A, you will need the other B and C parameters. Okay? So their concept is the sum type, and the idea is model data that is two or more distinct classes. Uh, so this is pretty common when we define in object oriented stuff, a kind of polymorphic stuff, but it's almost similar. We can do this. Great. keep it there. Um, etc. That's the idea. Model data that we have and polymorphic behavior, defining uh, objects or case classes that extends that on a superclass. We have subtypes of that, and we can start to talk about in terms of uh, a, is or in these terms is or the keyword is or in or whatever. That's the idea. Always we try to in functional stuff is pretty important. Try to use types for whatever that you build, because that way allows thinking a little uh, expressive way instead of thinking in how to uh, in what we should do. We could think in how to do. That's the keyword. So the idea is, you know, let's see now how working with ADTs. And the idea is, start to combine uh, the sum type, the sum type pattern, and the product type. Uh, and the idea is, construct or increase the combinations of data that we can have. So, for instance, um, for how working with ADTs. So exists a concept called structural recursion, and yeah, that's the idea. Uh, in pretty informal terms, is the process to breaking down data into small pieces. And the idea is reuse the stuff. We have two ways to implement the structural recursion. The first one is using polymorphic implementation. And the other is use pattern matching expressions. Let's see on a short, pretty straightforward example to think a little bit better. For instance, we have on a trait A with a definition whatever, and we have two classes. This is a way to define the common functionality foo using the polymorphic implementation. That means the particular implementation will be included within the subtype definition. This is pretty useful when we have to create a specific functionality uh, for any subtype that we define respect his abstraction. The other stuff is pattern matching implementation. So the idea is just an example. We can define type alias. Uh, yeah, it's just for uh, demonstrative stuff. Pattern matching. Yeah. The implementation for f in terms of b could be whatever. That's really doesn't matter for our example. Let's see. This is, oh, this is block. We try again. Let's do this. Okay. We need the definition for bits previously, but just for uh, an example is the same that we defined previously. But the idea is when we have an functionality f or type f that we really can include within our subtypes, we can implement the common functionality in the supertype. That's the idea with power matching implementation. So we have this is an example how we can work with ADTs. Uh, you know, at the moment, you have any question?
this handles diamond inheritance too, right?
Sorry, come again.
Yeah, diamond inheritance uh when a single class how does it say it? When there's a grandfather class, there are descends from from it descends two parent classes, and those two parent classes both are both are and then there's a grandson class that inherits from both parents.
Exactly. When the functionality could be common, we can abstract this, and we can refer our subtypes here. We can refer our subtypes here and provide the desired implementation.
Okay, thank you.
This allows us also have a less code to maintain. Instead of implement the f function in each class, we can abstract in a in a super in our super type definition. But yeah, it's pretty similar that you mentioned. Okay, cool. This is pretty useful when we start to find to modeling uh, our domains. It's pretty useful. Start thinking in these terms. Now let's talk about a little bit more about functions. It's functional stuff, and uh, we have to think the first citizen class in this stuff are functions. That means when we use a functional language, we can use functions as a values, which is pretty. It's a big difference with mainstream languages. So we have a higher order function, and in pretty informal way is it's a function uh, that allow receive other function as a parameters and can return other function as a result. So let's see this in an example. So our requirement is a function sum that takes two integers, and with this, and it's a particular function and a particular addition. I mean, if just an example. So we can see we have this hard code behavior. So the idea is, the new requirement is we don't want to include the square of each parameter and then sum. The new requirement says we need to uh, the cube, for instance, for say something. Let's try to define the cube for an integer n. So our with higher order functions, we can do this. We can now receive the function that we need as a parameter. Also receive the other stuff as we find previously. Now we apply the same function for the terms. You know, for calling the function, we can use here the definition. We don't have to do anything else, and also this. Also, we can do we can introduce behavior that we need without modifying the base code, which is pretty nice. This also, as you can see, we can now we can see an example when a function returns a function. But you have any question at this moment? Let's see. Let's see question again. The function in the parameter can go in any position. Yeah, you can do. You can use the order doesn't matter. Really, it's just for readable the function, and that's my choice. You can use yours.
Nice, thank you.
Cool. So let's see, for instance, it's let's do this. Method creation. It's a kind of calculator. We return the operation that it's a function. Let's do a couple examples just for say. The addition and we return uh, name, and also we have uh, body body our function. So yeah, and other, but just an example. Maybe it doesn't matter. Here we go. So we receive a name of the operation, and we return a function that defines that function. This is pretty common functionality if you think. We receive a row definition, and then we have to return a functionality. Uh, yeah, that could be the way. So as we can see, the type of our uh, math operation result is a function. That means you know, we receive the result as a function, and we call this as a function as we do usually. So, any question at this moment regarding to this to that stuff?
Can you do that in one line?
What do you mean doing?
The math operation just in one line, passing the last two parameters.
Yeah, absolutely.
Ah,
Same. It's covalent, and or we said the last session. This is on a referential transparency stuff. We can start to do, but yeah, this also introduced the other functional concept. Uh, it's called coring. This, we have let's back here. We have three parameters. We can define this in a different way. This concept comes from theoretical stuff regarding to functional. Let's see. Coring. Yeah, I think yes. Coring. And in lambda calculus, we can have a function with multiple parameters. That means we only could have one parameter per function. But in programming, probably this doesn't make sense. This is pretty straightforward, just for showing the concept. We can just for show you how it's working. So we can do this. And what do you think? Which is the type for this? What could be the type when you do this? Let's see. Type is a function that receives an integer and returns an integer. That means we split our function definition into multiple parameters, and the result of them is a function. We can do this. And here we go, the final result. We have the ability to send parameters grouped by functionality could be, or whatever we need. That's the idea. You have any question that could be really confused at the first time? Okay, cool. So let's see. The next concept is composition. Uh, as we see, or we could have seen in our calculus or math uh, subject, we have one function, compose another, and we pass x. That's the concept. Could, but this is pretty formal definition. That the idea is when we think in a functional stuff, always could be think in a function in terms of a function. So the idea is this g function could be an abstraction and start to compose with the others. And yeah, that's the way to introduce our modular stuff in terms of functions. That could be. So let's see an example. Pretty still simple. But then remember the underscore syntax. And also remember the lambda function syntax. Oh, yeah, here we go. Then the composition stuff or composition function could be old 5 after so this is an function. Five called, and then do this very less verbose. The compact syntax probably won't work because we have uh, for current stuff. We don't have all the parameters, and our signature is this. And here we go. This is the stuff regarding to composition. So the idea is see that we have multiple functions that we could compose in another stuff. So there is a bunch of functions that we can do. We can start thinking in that terms. This is pretty straightforward for testing. For instance, we can just testing that function isolated, and the other isolated could be pretty nice stuff to to start doing the things in a functional way. Do you have any question? If not, this is I think could be enough for today. The next session we will have more about functional patterns, and we'll start doing a little bit more code, real code probably. That's all for
Okay,
now.
thank you.
Awesome.
Thank you, Giovanni.
Okay, cool.
Thank you.
You guys.
You.
Thank you, Mo.
Thank you. Bye.